All right, thank you everybody for joining today. For today's webinar, Deploying mmWave to Unleash the Full 5G Potential. My name is Ben Stone and I'm with RCR Wireless News. Our speakers today will be Alejandro Holkman, Senior Vice President, Corporate Engineering, Ozge Koyman, Senior Director, Technology, Qualcomm Technologies, and Pau Castells, Head of Economic Analysis, GSMA Intelligence. Being a disruptive new technology, there are many important questions that mobile operators, service providers, and customers may have. For instance, what does the return on investment look like for deploying 5G mmWave? And how well does 5G mmWave work in large-scale deployments? In this webinar, we will address some of the most asked questions on 5G mmWave, and you will also get the opportunity to ask your own questions to our panel of experts. As a note, the webinar and slides will be made available for download after the presentation today. Please be sure to enter any questions you have for our speakers during the presentation, and we will do our best to answer them at the end or follow up after the webinar via email. With that, I'm pleased to give you Alejandro.
Well, thank you, Ben, for the introduction, and welcome everybody. Let me start with a brief introduction to mmWave. mmWave is a spectrum band between 24 gig and 100 gigahertz. And the exciting aspect of this band is really the amount of bandwidth available. Just for comparison, there's 25 times more bandwidth in mmWave than what's being used for 3G and 4G. Of course, the more bandwidth, the more capacity we have to handle a larger number of users. And with that, we're able to provide much higher speeds. And for quite some time, many thought that mmWave bands were really not suitable for mobile cellular communications because of the shorter propagation and the difficulty of getting a larger number of antenna arrays in a smartphone form factor. But the good news is that we've had tremendous progress over the last few years in this space, and we've been able to overcome these challenges. And today we'll go over the status of mmWave and the progress in terms of the device ecosystem, deployments, and the use cases. Next slide, please. This is the spectrum landscape around mmWave. It's an overview of the different bands that have been defined so far and the countries. We're not going to go over all the countries here, but this is a good representation. We have allocations across every continent, and almost every continent, there are allocations either being discussed or already allocated. And the interesting aspect on this is that there is a healthy ecosystem being defined around certain bands. For example, around 28 gigahertz, we have them in the US, South Korea, Japan, Taiwan, and around Europe and China. There's a lot of discussion. It's either commercial or being worked on around the 26 gigahertz band. So there are definitely good sets of bands that are going to be common across many parts of the world. Next slide, please. Now, where are we today on the 5G rollout worldwide? And let's start with the Americas. We've already have deployed on Sub-6. We also have deployed on mmWave. And in 2021, next year, we're looking at having both Sub-6 plus mmWave carrier aggregation. So that's really the next step after you do mmWave only. When you do carrier aggregation between Sub-6 and mmWave, you have almost the best of both worlds because you get the coverage of Sub-6 plus the high bandwidth of mmWave. Going down to Latin America, there's been some trials on mmWave and some very interesting use cases that are showing up in LATAM around fixed wireless access. In Europe, like I said, there is a good ecosystem around 26. And there are countries such as Italy, Finland, Russia, which have already launched. And in Europe, almost every country is either going through the regulatory process framework or have auctions planned, or they'll be directly ready to issue spectrum awards in 2021. And then China, we're excited about China going into mmWave. There's a lot of discussion right now in China, and we're excited. There's going to be the 2022 Winter Olympics in China, and they're looking at using mmWave to showcase the capacity potentially in stadiums and some of the sites for the Winter Olympics. So a lot of preparation going into the Winter Olympics 2021. I won't keep going with the rest of the countries, but pretty much every continent, Asia, of course, there's been launches, but every continent, every area has mmWave plans. Next slide, please. So this year has been really good for mmWave. We've seen this year the launch of flagship smartphones that include mmWave. The good thing we've also seen this year is that mmWave is not only on the top end of the devices, we are actually seeing it across multiple tiers. So that has been really welcome by the industry. And not only we have it available today on smartphones, but it's also available on PCs. There's modules available, hotspots, and CPEs for fixed wireless. Next slide, please. So let's talk about deployments. And the way we think about mmWave is we look at two separate categories. First, we look at the two separate categories are outdoor deployments and indoor deployments. In mmWave, it's difficult to get coverage from indoors from the outdoors. So the way we like to think about it is you do the outdoor deployment is outdoor to outdoor and indoor to indoor. And for example, on outdoor, we did a study where we assumed a one-to-one overlay on each one of the existing sites. And we were very surprised by that study where the coverage was close to 70% in some cases where the network was dense. There's a lot of concern on mmWave that because of the short propagation, that you would need a tremendous amount of sites. But you know, when we actually did the study and we actually put one-to-one on cities, what would be the coverage, we were pleasantly surprised that it's not really as bad as people think, and actually it's much better, and you can get immediate coverage close to 70%, and in some cases 80% of the outdoor coverage without any additional sites. The other side on the indoor deployment, indoor to indoor, we're finding a lot of use cases for really areas that need tons of capacity. And we're, in terms of availability of equipment, for example, there are sites that are pretty much the size of a Wi-Fi access point that you can use for indoor, and those are low power, so you can actually power them by power over Ethernet. So very easy to deploy in terms of potential for indoor deployments. Next slide, please. So here is some of the tests that we've done in terms of throughput. And this is a study we've done. This is with 400 megahertz. And this is some of the speeds that you would expect to get. You have some near cell, mid cell, and far cell speeds. The interesting thing with millimeter wave is that even on far cell, your speeds stay really fast. So you actually have, still above a gigabit per second on 400 megahertz of bandwidth. So it's, with millimeter wave, you either have it or you don't have it, but when you have it, is extremely good. And the challenge, of course, is so that you have it most of the time or all the time. And that's where some of the density comes into play. Next slide, please. So this is actual data that we've gathered from Ookla, which is the company that writes the speed test app. And this is how it's the crowdsourcing data of the average speeds that people are getting when they are on 5G millimeter wave. And you're looking at hundreds of thousands of devices reporting this kind of speeds. And for comparison, in the same location, this is what they would be doing if they were on LTE. So of course, tremendous amount of bandwidth. The speeds are just incredible. In comparison, we took similar data from hundreds of thousands of devices from the speed test app, and the average in sub-6 on 5G sub-6 is the one that is in the middle column across different cities. And we also did this in Europe as well for the 5G sub-6 networks that have been deployed there. So it's really a huge advantage for the operators that have deployed millimeter wave, the amount of traffic that they're able to push out. Not only that, but that is the whole freeing up of 4G spectrum that is highly it's highly congested. So you are able to free up a lot of the traffic on the 4G bands and really be able to push as much traffic as possible on 5G millimeter wave. The demand is certainly there. You see the user data being used using the high band spectrum. Next slide, please. So this is let's talk about what is the deployment thinking on millimeter wave. How, where would you put it first? How would you would use it? What are the use cases? And so we've been looking at this for a few years, and we're watching very carefully, also working with a lot of our operator partners. And right now, the first thing that we're seeing where millimeter wave makes a lot of sense is where there are dense areas. So in terms of outdoor deployments, right now, things like stadiums, transportation hubs, those are the ones where you're actually getting tremendous amount of benefit because you can put a few sites and you're actually capturing a huge amount of traffic. There are some, for example, in the US, we have more than 30 NFL stadiums that have all been either already deployed or in the process of being deployed with the millimeter waves. And I do have a stadium example later in the presentation. We have transportation hubs across the world. There are some transportation hubs in Asia where you have hundreds of thousands or if not millions, some stations have millions of people going through every single day, and this is where they're doing their video downloads, they're waiting for the next train. So these are perfect areas where you can actually do millimeter wave deployment. Finally is fixed wireless. This is where the cost of providing fiber is just not economically feasible. So reaching those homes wirelessly with fixed wireless access makes a lot of sense. And finally, I would also have an industrial IoT example where we're looking at factories and warehouses. Now on the indoor side, enterprises are also getting very interested, especially what has been happening over the last few months. The indoor capability of enterprises for providing millimeter wave, providing 5G to the employees so that they can have access everywhere. It kind of leads very well so that you have the experience when you're out of the office or when you are in the office. So let's go over some of the specific examples. Next slide, please. So let's talk about the indoor enterprises. This is the floor plan of the lobby in our corporate headquarters here in San Diego, California, where we put in a millimeter wave node in the lobby because we wanted to cover the front part of the lobby with millimeter wave and get the experience. So on the picture, on the right-hand side, in the top right-hand corner of the slide, you see our lobby there as seen from the G-Node B. And the slide below is as seen as you enter the lobby. And so we went ahead and said, okay, let's see how this performs. And it worked as expected on the front side of the antenna. This is where you have that green area. So basically you had very good coverage across all the front lobby. But it started getting really interesting when we went behind the antenna. So if you look at it, if you look at that little brownish area, we were getting really good signal actually behind the antenna, back where there's an elevator shaft there. And this is because of all the reflections. And this is really how millimeter wave is really able to do very well indoors. It just reflects across many surfaces, and you are getting very good coverage even behind the antenna, which is quite a bit of distance all the way to the other edge of the wall. Not only that, but we went inside some of the hallways there across the offices. So with just one site, we were very surprised on the amount of coverage that we had. And of course, we were getting throughputs of multi-gigabits per second. I think on the front side of the antenna, we were getting 3.1 gigabits per second, and this is at 400 megahertz of bandwidth. If you actually get to 800, it will be close to double that speed. Right now, we're just limiting to 400 because of the availability of equipment, but hopefully soon we will have equipment that is capable of the full 800 megahertz. But the good thing is just the way the propagation works with millimeter wave in an indoor environment, in a standard office environment, leads very well to a deployment that could be similar to Wi-Fi. We've done a test, I don't have it on this presentation, but we did a test where we actually deployed one-to-one a 5G millimeter wave with a Wi-Fi access point, and we were getting pretty much the same coverage. And so that could be a very cost-effective type of deployment because you could take out that Wi-Fi access point, you can put a Wi-Fi access point that also has millimeter wave, and you have a very, with PoE, so you have a very cost-effective way of millimeter wave deployment inside the enterprise. Next slide, please. The next one, as I mentioned, is stadiums. Again, this is where you have, of course, 100,000 people wanting to upload pictures and download the video of replays. This is a perfect area where you can really see the power of millimeter wave. Our team was actually responsible for the design of the last Super Bowl that was in the US, in Miami. And in that, we actually, it was the first Super Bowl that, that had millimeter wave. So we actually looked at what speeds we were getting and how it was working. And to start with, the best thing about it is that the amount of sectors that you need, it's really small compared to what you would need with 4G. We were able to cover the whole ball with only 8 sectors. And in comparison, the design for 4G had about 121 sectors. So right off the bat, there is a much different number of nodes that you need, just because each node can absorb so much capacity. And during the game, at game time, and halftime is really where you have everybody using their phones, we were getting 10 times the amount of throughput for people that were sitting in the bowl compared to LTE. And for those lucky ones that were in the suites, they were getting 3 times as much what they could get with LTE. And also the parking lots, we were doing, also had deployments on the parking lots. So it's a very, very interesting deployment, and to the point that now that is very well proven. Almost every stadium in the United States, large stadium, NFL stadium, will have millimeter wave, because that's really the way to go. Next slide, please. The next testing that we did, as I mentioned, is one of the transportation hubs and a railway station. And in here, we actually put a site, a millimeter wave node, in 28 gig with an SA. And again, this is where you can see the power of millimeter wave, where you're getting 3.6 gigabits per second. And this is with the full 800 megahertz bandwidth. So we were very excited to get this kind of speeds in an area where, again, very difficult to do and absorb with either 4G, distributed antenna systems. Just the current architecture that is used, or existing mode of dealing with this traffic, it just will not scale in the years to come. So millimeter wave is, again, the way you can actually absorb all that traffic from the users. Next slide, please. This one we are super excited about. This one is about how far can you take a millimeter wave signal, especially for areas that are hard to reach. We had a good collaboration with US Cellular here in the US and Ericsson, where we say, okay, how far can we really take a millimeter wave signal with a high power CPE? This is not a regular smartphone, but it's a high power CPE. It has a much more advanced antenna, different antenna gain, and but it's still it's a CPE. And we said, okay, same base station, how far can we take it? And we were extremely pleased to see that we could take this all the way to 5 kilometers and still get 200 megabits per second. This would be areas where just deploying fiber is just not economically feasible. We had a lot of interest from a lot of operators around the world on this test, on the different ideas that they have that they could do. Of course, this was line of sight. but there's many cases where line of sight is still good enough, and if it's not good enough, you try to figure out how to get line of sight. Or like my colleague Oski will talk about later, you might be able to do IAB or multiple relays where you actually get to potentially a line of sight scenario. Now, if we didn't have it, then of course, you might you can go shorter distances. In shorter distances, we still got 2.1 gigabits per second at around 1 kilometer. But this opens a whole field of possibilities for use for millimeter wave that might be on an existing site. So it's additional revenue opportunities for the operator using potentially their existing assets, their existing cell sites. Next slide, please. And the last use case that I have is the one for a factory floor. This is something we've worked with a factory in Asia, and they want to do a smart manufacturing plan where they will have automatic inspection of product lines with AGVs. This is a case where they will have video, actually high definition video that they want to upload across all the aisles between the machines. They want to have augmented reality where they want to have pretty good speeds. And this is the deployment scenario. It's a pretty large manufacturing floor, about 34,000 square feet. And so basically we put, you know, a few sites in certain locations, and sometimes you may have blocking, so you may need additional sites. I believe this is maybe a little bit over-dimensioned. We could have probably done with less, but still a very, very equivalent to Wi-Fi in terms of where you might need potentially have access points. But the speeds we're talking about, even though the initial use cases are relatively small in terms of speeds, you can actually achieve, right now it's 1.5 gigabits per second, but if you had, again, this is only 400 megahertz. If you had double the bandwidth, you get roughly double the speed. And the reason we had so many sites, as the slide shows, is just the amount of coverage. We wanted to make sure we covered every single corner of that factory floor, anywhere where the AGV could go. This is a similar use case that we're hearing for this is warehousing, where you want to go to absolutely every single corner of the warehouse, and being able to have automated inventory systems, automated AGVs, to retrieve warehouse items and inventory. And there's also, of course, position location advantages when you have a certain amount of sites with a more accurate position that you can actually do with 5G. So with that, this is my last slide, and we have a lot more to talk about in this subject, so be sure to tune in next Tuesday, the 17th, for the second part of our webinar, where we will have a lot more information around field testing. And with that, I will pass it along to my colleague, Pau Castells from GSMA Intelligence, who will talk about the economics for around millimeter wave deployments.
Thank you, Alejandro. It's a pleasure to be here today, and we will be presenting the first results of a new study that we are still conducting. We're in the final phase of analysis, and we will be looking to publish in just a few weeks. What we do in this study is we look at and analyze in detail the cost effectiveness of millimeter wave 5G solutions. Next slide, please. First things first. So a quick introduction to ourselves. We are GSMA Intelligence, the research and analysis branch of the GSMA. As many of you will know, we are a global association of mobile operators. And GSMA Intelligence, as a unit of the GSMA, is a leading provider of research, analysis, forecasts on the mobile industry. And as part of our research agenda, we are closely tracking 5G and millimeter wave deployments. And I'll talk today about this new study, tackles this crucial question. So when and where will it be cost effective to deploy high band spectrum for 5G? And what's important to note is that we don't look at it from a futuristic perspective. We do it by identifying a range of scenarios where it does make sense in the short run. And then for each scenario, we explore the different conditions under which these deployments could be cost effective. Next slide, please. 5G is now a commercial reality. Despite COVID-19, adoption of 5G will reach more than 200 million connections globally by the end of next month. And we'll have by then nearly 150 operators that will have launched 5G services globally. This is forecast to grow quickly to nearly 2 billion connections on 5G globally by the end of 2025. And obviously, to accommodate this rapid growth in adoption in the next 5 years, operators will be investing very significantly in 5G networks. In this period, 2020 to 2025, we expect operators to be globally investing in excess of $1 trillion in networks, of which nearly 80% of that will be on 5G. And it is precisely for that reason, these huge costs required for 5G, that we carried out this study to understand the most cost-effective way to deliver 5G services under a range of scenarios. So most 5G launches globally so far have relied upon mid-band spectrum between 1 and 6 gigahertz, with the 3.5 gigahertz spectrum band being the chosen one in many countries. But as 5G adoption grows, we will need more capacity to support 5G very soon. And this will need spectrum across low, mid, but also high millimeter wave bands. As Alejandro mentioned, thanks to the massive spectral bandwidth available in these bands, they are going to be key to meet the high traffic demands and at the same time maintain the performance and requirements of many of the 5G services. I'm not going to go into the detail of what countries have launched. The only thing to have in mind and to highlight is that millimeter wave spectrum is already available in a good number of countries, including the US, South Korea, Singapore, Thailand, and a few others. More countries have already announced plans to release the band very soon. And what's quite remarkable about it all is that millimeter wave spectrum was only allocated as a harmonized band for mobile just a year ago in the recent World Radio Communications Conference last November. So in just a year, we have seen quite a lot of good progress in the release of the band. Next slide, please. So despite all these positive developments, when it comes to spectrum assignments, millimeter wave has some challenges. They are well known. So millimeter wave signals travel relatively short distances. They can be susceptible to interference from trees and other obstacles. They have difficulties penetrating building walls, which obviously are necessary to reach indoors. And finally, they largely involve new deployment strategies, involving more small cells, which present some, not necessarily challenges, but some novelties from an operational and logistical perspective. However, mobile data traffic is growing very fast, and that plays to the strengths of the band. Millimeter wave bands can accommodate more capacity and bandwidth than any other band. But before any deployments can be carried out at scale, we need to be market ready. And millimeter wave 5G is now starting to achieve the scale that is needed to reduce deployment costs. We'll look at that from next slide, some signs of market readiness. First, an indication, a clear one, of the readiness of any particular spectrum band is the number of trials that have been conducted on it. and the overall number of trials in millimeter wave bands now exceeds 100, which shows that the technology is reaching a more mature stage. And our confirmation of this maturity is that we already have 4 operators in 3 countries having launched commercial 5G networks using millimeter wave bands. Next slide. And another sign of market readiness is having a sufficiently wide ecosystem of consumer devices and equipments. And consumer devices in particular have shown very good signs of progress very recently. So while last year, in 2019, only 5 millimeter wave handsets and 5 FWA CPEs were available, next year, in 2021, consumers can expect more than 100 millimeter wave 5G handsets and more than 50 FWA CPEs to be available. And a similar story is also unfolding with network equipment. So we also have some very encouraging signs there. All major equipment vendors are now offering millimeter wave equipment products as part of their portfolio of solutions. There are a range of product categories available already. And quite importantly, the cost gap with mid-band solutions is also decreasing steadily. Next slide. So as we have seen, the millimeter wave ecosystem is now reaching maturity. There are devices, there is equipment, and there is spectrum. The key question is when and where it will make sense to deploy millimeter wave solutions for 5G. That's what we have done in this study. So we look at the total cost of ownership of 5G networks, aka the TCO of 5G networks, and we analyze it in detail. TCO depends on several factors. First, it depends on the cost of the equipment, which right now are a bit higher for millimeter wave, but also on the traffic demand. More traffic clearly plays to the strengths of millimeter wave, and also how this demand is distributed in a given area. And more concentrated, the better for millimeter wave. In our study, we identify a range of scenarios where the range and high throughput of millimeter wave can lead to cost-effective deployments in the period to 2025. And we then explore and dissect, in a way, the conditions under which these deployments could be cost-effective. And we have some of the preliminary results in the next 3 slides. First, we have looked at a dense urban scenario. Particular 2 dense urban areas, one in Europe, another one in Greater China. In both cases, what we do is we build this dense urban area by using real data from cities in these 2 regions. And we then consider 2 different deployment strategies. One where mobile traffic is just met with 3.5 gigahertz solutions with mid-band spectrum. The other where 3.5 and millimeter wave are both available. And then we look at the period over the next 5 years to understand where it's most cost-effective to deploy using one strategy or the other. What we find is that millimeter wave can be cost-effective when deployed alongside 3.5 by providing an additional capacity layer in the densest parts of these cities. In the case of Greater China, we estimate that deploying millimeter wave solutions could be cost-effective pretty much as soon as spectrum is widely available for commercial deployments. In dense urban Europe, we estimate that millimeter wave 5G solutions in the densest parts of urban areas could be cost-effective from around 2024. And in the case where traffic demand is relatively high, as we can see in the chart. Next slide, please. The second scenario that we looked at was 5G FWA. Here we looked at 3 quite distinct and different areas. An urban area in China, a suburban area in Europe, and a rural town in the US. And again, we compare two alternative deployment strategies, one with 3.5 gigahertz, another one with millimeter wave. What the preliminary results show is that deploying a 5G fixed wireless access network using millimeter wave can be cost effective in this period, but this really depends on two critical factors. First is how fast the data traffic grows in the residential broadband market. The faster it grows, the better for millimeter wave solutions. And the second factor is that it depends on the share of households that can actually subscribe to a 5G fixed wireless access subscription in a given area. So that's another factor that is important. So back to what Alejandro was mentioning, in areas where the reach of more traditional fiber connections for residential broadband are more difficult or less available, that's where obviously 5G FWA for millimeter wave makes more sense, and where it can be more cost effective and more secure in reaching that level of take-up. Next slide, please. And finally, the third scenario that we have looked at is an indoor office scenario. So this is a large office, and we assume that in this office, indoor coverage is relatively poor, so that only a relatively small share of traffic on 5G can be offloaded to outdoor sites. And again, we look at the two alternative deployment strategies, one just with 3.5, another one with both 3.5 and millimeter wave. And the results, they show a clear picture where indoor 5G networks can be cost effective and generate cost savings when a significant share of data traffic is supported by indoor 5G services. The chart here shows that when about 30% of devices in the office are supported by indoor 5G, millimeter wave is cost effective when compared to an alternative 5G deployment strategy. Next slide, please. So this is a summary so far of some of the TCO analysis that we have looked at in the period to 2025. As a final remark, I wanted to also highlight how we expect millimeter wave 5G deployments to accelerate further in the second half of this decade. By 2030, our macroeconomic models show that 5G alone will generate an annual boost to global GDP of more than 600 billion. And the millimeter wave will be playing increasingly a key role in the delivery of these benefits. Next slide, please. And that's the last one I have. Want to leave you with a few thoughts, because the results of the TCO analysis mean different things for different stakeholders. So for mobile operators, the key thing is here that you should not underestimate the role of millimeter wave in the short term. So adding a capacity layer with millimeter wave to offer 5G solutions can be cost effective under a significant range of scenarios in the short run. So operators that do not have access to this spectrum or that have not sufficiently tested these solutions yet, they run the risk of finding themselves potentially at a disadvantage in this early phase of 5G rollout. Governments and regulators across the world are also looking to capitalize on 5G as sometimes a catalyst of economic growth. And with millimeter wave playing a key role in 5G, this means that sufficient millimeter wave spectrum in the right conditions needs to be assigned. And while we've seen, millimeter wave spectrum is now becoming more widely available, many countries have still to develop clear plans for the assignment of the band to mobile services. So without it, governments run the risk of potentially creating inadvertently an artificial barrier to the development of 5G networks. And finally, and despite the momentum, the last one on the vendors. So despite the momentum and market readiness, vendors need to continue to improve products readiness for millimeter wave 5G. And a wider choice of devices and equipment will reduce deployment costs and will facilitate greater adoption. And next slide, please. So that's all I wanted to share today. Thank you very much. I hope it has been useful. Please look out for the publication of the full study in just a few weeks' time. And I'll hand over to my colleague Osge Koeman from Qualcomm. Thank you.
Thank you, Paul. Good morning, everyone. So I'll spend the next 10 minutes or so covering briefly where we came from, what we're currently working on in 3GPP, and then the future roadmap for mmWave as we continue to improve it and expand it. I should note that I'll be lightly touching on a lot of these topics, but early next year we do have another webinar that we're planning where I'll get to have a deeper dive on many of these. So as we know, release 15 was really the foundation of the 5G release. It was highly parameterized, provided an opportunity for us to expand and grow into new use cases and new spectrums, with the initial focus being eMBB and fixed wireless access, which is driving all the early deployments that have been mentioned so far. In future releases, release 16, release 17, and beyond, we of course continue to evolve eMBB and fixed wireless access. We improve certain metrics, improve coverage, improve the power consumption. It's improve the beam management, so reduce latency of certain things. So that's an ongoing effort. In addition to opening up new use cases for mmWave. One that was mentioned is, of course, industrial IoT, where we're bringing mmWave into factory spaces. And then somewhat closely tied to that is also positioning, where we head towards centimeter level accuracy positioning. And then we also have been trying to address the deployment aspect of mmWave through integrated access backhaul, IAB, which I'll dive into in the next few slides. So future expansion for release 17 and beyond continues. We're looking at new spectrum, which of course has its new challenges, so 60 gigahertz and beyond, making sure that the air interface is optimized for new applications like XR, and then on the other end, also bringing mmWave to very low cost devices, so these reduced capability devices, which could be security cameras or other very low cost devices, so that mmWave is across a spectrum of use cases and devices. So next slide, please. So one thing that my colleague Alejandro was mentioning is that mmWave does have certain issues that we have to address in terms of deployment. So we really have to think with a new strategy for deployment to make sure that we get the coverage that we need, and that each geographical location has enough density of beams. So there's a diversity of beams that can provide more robustness and coverage. So you're really trying to get this kind of line of sight type of links where maybe reflectors don't happen, or where there might be a lot of blockages. You want to make sure you have a diversity of beams. So that's something that we've approached in a number of ways. Some of these involve standardization. Some of them just involve the strategy for deployment. And in some of these we've actually shown in our years of MWC demos, if you've seen any of those, trying to validate a lot of these ideas. On the left side of the screen, you'll see that that's one strategy that you can have, where you have this distributed remote radio head, so a single GNOB connected with remote radio heads that are across space, and that's something that we showcased actually in this past MWC. And those connections could be either wireless front haul or fiber front haul, and they provide just diversity across your whole deployment area. In the middle, we have repeaters, which are receiving a lot of interest in the mmWave in the last couple of years, where we have different types of repeaters. On top, I show a simple repeater, It could be active or passive, but it's really just amplifying the signal and maybe sending it around a corner or trying to out to in, but there's really no smarts in it. And then below that is the smart repeater concept, where there would be some TDD awareness and some kind of beam management, so some adaptive multi-beam operation that provides you higher gain and ability to track UEs even from a repeater side. So that's obviously not a standardized thing, but it's something that we're trying to make sure will get standardized. So it's up for discussion in 3GPP right now, and there's certainly value in a device like that. On the right side is integrated access backhaul, which you can view as a digital repeater in a sense. But each of these IAB nodes is a base station in itself and manages the local users and adds capacity and coverage to the network. So I'll dive a little bit further into IAB to show some of the features and where we're going with IAB. So when an operator wants to deploy millimeter wave, obviously they have existing eNode B sites, and as Alejandro had mentioned, they'd like to co-site with those sites, and they have fiber backhaul to those sites. But further densifying in certain areas is cost prohibitive. We're running fiber to all the different small cell locations can be a deterrent to deployment. What they do have is, of course, the millimeter wave spectrum, which they can share across backhaul and access. And the interference can be limited given the characteristics of millimeter wave. And so for a single GNode B shown on the left side, that GNode B can actually support multiple IAB, so integrated access backhaul sites, where in the standardization, the spec, we support multi-hop capability, redundant links, and then going into release 17, full duplex operation, and a number of other innovations to make this a very efficient, cost-effective deployment. So now the small footprint of the GNode B has expanded quite a bit and approaching the footprint of a sub-6 eNode B with these additions of these IAB nodes. And next slide, please. Yeah, so for the operator, what kind of advantage does this give? So there's a nice strategy here. On the left side, we have the co-siting, co-location, initial deployment. So operator has eNode Bs and they have fiber backhaul. They'd like to co-locate the new millimeter wave deployments on those sites. But in some places, some cities around the world, some locations in certain countries, you don't really have the density to provide enough coverage just by co-siting. And running fiber to all those little all the new locations is cost prohibitive. So what they would want to do actually is put IAB nodes on all the new locations to provide the coverage that they want, being served by those fiber locations. So this at least provides the initial coverage, provides the service. And then over time, as data demand grows, then the operator will actually start adding fiber drops to more of these IAB nodes. And in the extreme, you might actually have to have fiber drops to all of these to provide the capacity needed. Okay, next slide. So we've shown this in the past MWC. We want to actually show a simulation of this, the advantage that this IAB brings. We did target a European city that was not highly densified for eNode B, and so it didn't really suit millimeter wave. We picked Frankfurt, so a kilometer squared, and we show that different types of IAB penetration, low to high, so 14 IAB nodes to 20 to 28 IAB nodes, provide significant coverage and throughput advantage, particularly in the the tail users that were somewhat out of coverage or at the edge of coverage. So there is a link here for a full demonstration of this video. I encourage you to watch it to get a more in-depth presentation, but I'll skip it for now, just given the amount of time. So next slide, please. Of course, we've, like I mentioned, we validate a lot of these ideas in our network, and we present some of these in MWC. You know, we've validated the multi-TRP concept to help what kind of robustness and coverage that gives you. Validated high-speed mobility. In this case, we just used a drone, and made sure that new applications like VR can actually be supported on a 5G network. And again, there is a video of this as well. You can also watch that and get an in-depth analysis of you know, our network, as well as some of the other simulations that we did. Next slide, please. So I'll spend a little bit of time on this slide, just to show, you know, what are the completed release 16 projects, and then release 17 and beyond, you know, where we're actually going. So some of the completed projects, you know, outside of eMBB and fixed wireless access, of course, we mentioned this integrated access and backhaul. But for a UE and CP type of use case, we've continually enhanced the beam management, improved the latency robustness, enabled multi-TRP in the network, optimized the power, you know, with control channel monitoring and CDRX improvements, and then improved positioning, which is heading towards centimeter level accuracy in the next releases. So for release 17 and beyond, IAB continues to improve. You know, we are looking at you know, full duplex right now in release 17. We'll continue with multi-hop QoS improvements, potentially mobile IAB, even unlicensed IAB, IAB Lite, which would be like a smart repeater. So that continues to evolve. And then we're expanding into new spectrum. So we're not stopping at 28. We're looking at 60 gigahertz right now. DGBP will consider up to 114 gigahertz. And all those bring new applications and new use cases, front haul, back haul. So that millimeter wave will continue on that aspect. And then, of course, new use cases like industrial IoT, in addition to side links, so device to device, URLLC, all those you know, have a use in for millimeter wave. I think I'm probably out of time, so I'll stop over here and just open up, allow some time for questions.
Super, yes, thank you so much. Yeah, so there are lots of great questions from the audience. Unfortunately, we will only have time for a few, but I would like to start with a question from the audience. So, have motorway environments been looked at in terms of infrastructure requirements? This question is for Alex.
I'm sorry, you said motorways?
Yeah, sorry. Have motorway environments been looked at in terms of infrastructure requirements?
I'm assuming you mean just road
Highway
type, yeah, highway type. Yeah, I mean, there is a whole area on 5G that is CV2X that has to do with the whole communication with the automobile. I won't get into that much right now, but hopefully we can have a webinar on the subject. But there's a lot of things that are happening that could provide both for an infrastructure, both for highways and also for vehicle to pedestrian and vehicle to car kind of infrastructure. So there's a lot of these things coming together.
Okay, great. Another question from the audience. How does the factory G node B compare with the outdoor G node B? Is it the same product?
I can take that if very quickly. On an indoor requirement, for example, on a factory, you have to look at things like reliability. If you're going to use this, for example, for a production line. And an outdoor G node B, you might need potentially a larger number of antennas, more power than an indoor G node B. So same technology, but you may have different types of requirements.
Super, thank you so much, Alex. And then I guess I'll ask one last question. Thank you everybody so much for sticking around. Is there any difference in range, performance, or other things as you change bands? How about 60 gigahertz E-band and beyond in the range of 100 plus gigahertz?
Sure, maybe I can take that. So there certainly is a difference because all those bands have different characteristics in terms of reflection and penetration loss. And then, so when you take the average of all that, in a certain type of deployment area, there will be a difference. So if you go all the way up to, say, 95 gigahertz and you look at an urban deployment, there will certainly be a propagation difference especially in non-line of sight type of situations. So the cell sizes might start shrinking as you go higher and higher in frequency. But that doesn't mean we can't get it to work. It's just the cell sizes might shrink, and there's certainly a place for all those bands in the future.
Okay, wonderful. Well, that does conclude our time for this webinar today. I want to thank the three panelists so much. Qualcomm, thank you as well. And just a note to all of our attendees, there is going to be a second part to this series next week, November 17th, same time as this one. So thanks again to Alex, Pao, and Oscar.
Thank you.